Okay, in continuing on with the inverse of a matrix, okay, we had that if A is an invertible matrix, then the inverse of A is also invertible, and we have the inverse of A comes out to A itself. And again, we looked at earlier that the product between A and its inverse and vice versa will come out to an identity matrix. All right, now we have for the next portion, okay, if A and B are n by n invertible matrices, that is where we have the same number of rows and columns, that is we have number of rows and the number of columns will be one and the same, so we have square matrices. Okay, so if we have A and B to be invertible matrices with dimensions n by n, so will the product AB, and the inverse of AB is going to be the product of the inverses of A and B in reverse order. So we have for the inverse of the product of matrices A and B, this will be equal to the product where we have in order the matrix of B inverted times the inverse of matrix A. All right, and also we have that if A is an invertible matrix, okay, then so is okay, A when transposed, and the inverse of the transpose of A is going to be the transpose of the inverse. Okay, so the inverse of the transpose of A is equal to the transpose of the inverse of A, and we'll be looking at samples of these last two items. Now, and let's say that if I'm looking for the inverse of the product matrices A and B, and I have given that A is at 1, 3, 5, 7, and I had that B is going to consist of 3 and 5 for the first row, 7 and 9 for the second row elements. So we have for the inverse of A, again using our algorithm, we have 1 over AD minus BC. So you have 1 over 1 times 7 minus 3 times 5, or 5 times 3. And again, we have D um, um, to be at 7, and then we have in this particular case we have negative B, negative C to respectively be at negative 3 and negative 5, and again we have A in the bottom right hand corner. So we have for the resulting fraction we have negative 1/8 and distributing over 7, negative 3, negative 5, and 1. It turns out that for the inverse matrix A, we're going to have negative 7/8 and 3/8 at the top, and at the bottom we will have 5/8 and negative 1/8. And for taking what we have for the inverse matrix B, so you have 1 over 3 times 9 minus 5 times 7, and again flipping the diagonals and taking the opposite signs of B and C, we have for the result, again we have the fraction to also turn out to be negative 1/8 and distributing over 9, negative 5, negative 7, and 3. It turns out that for the inverse of B, we will have at the top negative 9/8 and 5/8, and for the bottom row we will have 7/8 and negative 3/8. And now for the determination of the inverse of the products of, or the product of A and B, okay, again, so we're looking at taking the products of the inverse B, and that which you have in the inverse of A. And so again, so the inverse of B, again we have this 2 by 2 matrix. Inverse of A, we have again negative 7/8 and 3/8, as well as 5/8 and negative 1/8. And just taking the inverse of B and multiplying the first column from the inverse of A. So we have in this manner treating the negative 7/8 and 5/8 as weights. So you have negative 7/8 over the first column from the inverse of B, and you have plus 5/8, the second weight, times the second column from the inverse of B, and combining what we have here and reducing. This will come out to 11/8 and negative 1. And if I take the inverse of B times the second column of the inverse of matrix A, so the second column from the inverse of A, I have 3/8 and negative 1/8, and again treating the 3/8 as the first weight to go over the first column from the inverse of B, and negative 1/8 as the second weight, which will be distributed over the second column from the inverse of B, and combining. Okay, once we combine the top and bottom layers and reduce, okay, it turns out that we have for the result at the top we have negative 1/2 and at the bottom we have 3/8. Okay, and so fusing together, it's going to turn out that the inverse of the product of matrices A and B, we have the inverse of A times B. Again, this will be equal to the product of multiplying the inverse of B times the inverse of A. And we have for this final result, we will have at the top row, again, you have 11/8 and -1/2. And for the bottom row, we have -1 and 3/8. All right. And now, for what we have regarding transposes. Okay, say if we have showing that the inverse of the transpose of A is equal to the transpose of the inverse of A. And let's say just with the very first matrix we worked with, okay, for section 2.1, we had the A was equal to 1, 2, 3, 4. And when we were looking at determining the inverse of this matrix, we had -2, 1, 3/2, and -1/2. Now just putting what we have in terms of transposing. Now for A, again, you have the transpose. Say if you have first column becomes the first row, second column becomes the second row. So the transpose of A, we're going to have it 1 and 3, 2 and 4. And for the inverse of the transpose of A, okay, so you have working with the diagonals. So you have 1 times 4 minus 2 times 3. So you have 1 over that difference. So we have 1 over -2, which would be -1/2. And again, flipping the diagonals 1 and 4 and taking the opposite signs of 3 and 2. So we have -1/2 over 4, -3, as well as -2 and 1. For that output, we have -2, 3/2, 1, and -1/2. And for the transpose of the inverse of A, okay, so making the first column into the first row, I have -2 and 3/2. Making the second column into the second row, I have 1, -1/2. And guess what? The inverse of the transpose of A with its elements, and for the transpose of the inverse of A, it turns out that we will have the very same values and positions. All right. Now, moving on. Okay, now if you're looking at something that not just for 2x2 matrices, but you might have square matrices that might have more than 2 rows and 2 columns. And let's say that for your algorithm for finding the inverse of a matrix, okay, it says here, if we look at going back to row reduction, it says to row reduce the augmented matrix, okay, where we have what is given for A and you have I. And if A is row equivalent to I, then we have for the augmented matrix, this is going to be row equivalent to I and where we have the inverse of A. Otherwise, A does not have an inverse. And now there'll be quite a few steps in the process, and it will sort of flex your muscles once again in terms of looking at reduced row reduction or reduced row reduced echelon form. And now, say if you have a given matrix A where we have 2, 4, 6, 0, 0, 3, 0, 1, 7, and we want to find out just what the inverse of A is going to be if it exists. Okay, so putting what we have for A and putting in terms of the augmented matrix, okay, where we have the identity 3x3 matrix included. So again, we have 2, 4, 6, 0, 0, 3, 0, 1, 7 on the side of A. And for the identity matrix, I have 1, 0, 0, 0, 1, 0, 0, 0, 1. And if I make the left-hand side into the identity, okay, so what I'm going to do here, we have 2, 4, 6 at the top, and I want to make this 2 into a 1. So I'm going to take 1/2 of the first row, so that's going to affect everything in the top layer. Everything for right now is going to remain fixed. So the top row becomes 1, 2, 3, 1/2, 0, 0. Okay, so we have, again, so we have the first pivot position to be at 1, and again, immediately underneath we have at zeros. Now, for the next pivot position, I want this to be the second row, second column element, okay, and I want this to be a non-zero value. And here, in terms of moving, I want this one to stay in the corner, but for the one at the bottom, I want to move this over. So what I'm going to do here is I'm going to flip the R2 and the R3, so third row becomes the second and vice versa. So we have in the rewrite, have 1, 2, 3, 1/2, 0, 0. Second row transposing, have 0, 1, 7, or I should say, yeah, have 0, 1, 7, 0, 0, 1. Third row, we have it 0, 0, 3, 0, 1, 0, and say that in continuing. Okay, so we have for the second column, okay, I have 0 beneath it, and I want to make this 2 likewise into a 0. So what I can do here to make this 2 go to 0, I'm going to take 2 minus 2, and this will be through the pathway of saying that we had the first row minus twice the second row elements. So here we have in the layout, the first row is now going to become 1, 0, negative 11, 1 half, 0, and negative 2. And again, this is taking all of twice, so 0, 1, 7, 0, 0, 1 from the respective parts from the first row. So we had this development. Now for the next pivot position, this will be where the 3 is located, and I want to convert this into a 1. So I'm going to take 1/3 of the third row elements. So we have leaving the first 2 rows the same for right now. Last row we have it 0, 0, 1, 0, 1/3, and 0. Okay, so in carrying over, all right, so we have for R1 and R2, okay, so we have our third pivot position. We have the 1 at the bottom, and I want to make the negative 11 and the 7 into zeros. So I'm going to take, to go from negative 11 to 0, I'm going to take negative 11 plus 11, and to adjust everything in the top row, I'm going to have R1 plus 11 times the third row. So I have, in the process, I have 1, 0, 0, and on the other side, I have 1 half, 11/3, and negative 2. And to convert the 7 that we have in the second row to a 0, I'm going to take away 7. So I'm going to take second row elements and deduct 7 times the last row. So I'm going to have 0, 1, 7 minus 7 becomes 0. And then we have going across, have 0. And 0 minus 7 times 1/3 will be negative 7/3. And we still have 1 at the very end. And the bottom row, okay, we have to remain fixed at 0, 0, 1, 0, 1/3, and 0. And if you notice, okay, just after the adjustment, okay, if you notice for what we have on the left-hand side, that is our identity matrix. And then for what we have on the right-hand side, this will be the inverse of A, which we will have to come out to where the top row will consist of 1 half, 11/3, and negative 2. Middle row we have 0, negative 7/3, and 1. And for the bottom row we have 0, 1/3, and 0.